Welcome back everyone. Today we'll be doing the second half of Unit 2 Algebra. Let's start with quadratic sequence. Not like arithmetic sequence or geometric sequence, quadratic sequence is in the form of a x squared plus bx plus c, which is a quadratic expression. And x here is our term number, which is also n. So a simple quadratic sequence could be like this: 1, 2, 4, 7, 11, 16. We can see that the difference is jumping. Plus 1, plus 2, plus 3, plus 4, and plus 5. Now this is a typical quadratic sequence because the difference of the difference is constant. Now to find the expression for a quadratic sequence, first we can do it by solving simultaneous equations. Because we have 3 terms and we have 3 variables. We know that when n equals 1, which is x equals 1, a plus b plus c equals 1. And when n is 2, x equals 2. It is 4a plus 2b plus c equals 2. And the same for when n is 3. 9a plus 3b plus c equals 4. Now we do this by subtracting equation 1 from equation 2, which we get 3a plus b equals 1. And we can deduce that b equals 1 minus 3a. Then we minus equation 3 by equation 1. We'll get 8a plus 2b equals 3. Substituting b equals 1 minus 3a, we'll get 8a plus 2 times 1 minus 3a equals 3. Expanding this, we'll get 8a plus 2 minus 6a equals 3. Moving the a's on one side, the constants on the other side, we'll get 2a equals 1. Thus, a equals 1 over 2. And substituting the a value back here, we'll get a equals 1 over 2, b equals 1 minus 3 over 2, which is negative 1 over 2. And bringing these two values into equation a, we'll get c equals 1. So the expression will be something like half n squared plus negative half n plus 1. We can verify this by substituting the values of n. So n equals 1, we'll get half minus half plus 1, which is 1. N equals 2, we'll get 4 over 2 minus 2 over 2 plus 1, which is 2. N equals 3, we'll have 9 over 2 minus 3 over 2 plus 1 equals 4. Now moving on to change the subject. So sometimes you could have the expression y equals 3x plus 1, and you want to make x the subject, which turns this into x equals something something y plus something something. So you do this by trying to make x the subject. So in this example, what we do is y equals 3x plus 1. We first subtract 1, we'll get 3x equals y minus 1. Then divide by 3, we'll get x equals 1 over 3 times y minus 1. A harder example could be y equals x over x plus 1. You do making the x of the subject, you first multiply x plus 1 on both sides. We'll get x plus 1, y equals x. Then we expand the left side, we'll get xy plus y equals x. We move the xy on the other side, we'll get y equals x minus xy. Then we take out the x on the right side, we'll get y equals x times 1 minus y. Then dividing the 1 minus y, we'll finally get x equals y over 1 minus y. And when we have higher powers, for example, y equals 3x squared plus 6x plus 3. We first will complete the square for the quadratic here. So we first divide this by 3. We'll get x squared plus 2x plus 1. And we complete the square inside, which is 3 times 2a is 2, so a is 1. X plus 1 squared. Now into minus 1 and plus 1. So this is actually already a square. So we'll get 3x plus 1 squared equals y. Now we first divide this 3, makes it x plus 1 squared equals y over 3. Then we root both the sides. We'll get x plus 1 equals square root y over 3. Thus, x equals square root y over 3 minus 1. Now functions. Functions is just another way to say y equals. Instead of y equals 3x minus 5, now we have fx equals 3x minus 5. This is better because we can save a lot of steps. We first declare fx equals 3x minus 5. Then we can say f3 equals 4. Just simply changing the x here will do the job. f9 equals 22. Instead of writing 3y equals 3 times 3 minus 5, all the whole equation. Here are some examples of functions. For example, g here. Gx equals 3x plus 4 over 5. So G2 is 3 times 2 plus 4 over 5, which is 18 over 5. And h here, the same. hx equals 2x squared plus 3. And h2 equals 2 times 2 squared. 2 squared plus 3, which is 8 plus 3, which is 11. Now there's a thing called composite functions. For example, we could have something like this, g, f, x. This means g with the x being fx. Now we know that gx is 3 times x plus 4 over 5, and fx equals 3x minus 5. So how this works is instead of x or any number, you put 3x minus 5 as dx. So g fx gives us 3 times fx, which is 3x minus 5, plus 4 over 5, which equals 3 times 3x minus 1 over 5. This is simple. So we just put the inner function into the outer function. And composite function can be very long, like g, g, f, f, h, g, f. So if there's a number, you just put the number in. If there's no numbers, it would be something like this. Just express it in x. So we already have gfx equals 3 times 3x minus 1 over 5. We want to know what is gf2. One way, just substitute 2 for x here, which is 3 times 3 times 2 minus 1 over 5, which is 3 times 5 over 5, which is 3. Another way, since it's a composite function, we could first find f2. f2 is 1. Then we use d1, the output of the function f, as an input of the function g. So we calculate g1, which is 3 times 1 plus 4 over 5, which is 3. Another important thing you need to know about functions are the inverse. So an inverse looks like this, with a -1 on the top, which means when you put in let's say y, you'll get the x. So you can see function fx as a program. When you put in an x input, you get a y output. Now the inverse of fx is the exact opposite of fx, which the input, if you put y, you'll get x as the output. So how to find the inverse of a function? You just simply change its subject. For example, we have fx equals 3x minus 5. We want to find the inverse of fx. We change the subject from x to y. So y equals 3x minus 5. We want to make x the subject. We first plus 5. Y plus 5 equals 3x. And then we divide 3. X equals y plus 5 times 1 over 3. So the inverse of fx, remember it's x here, so it still has to be x, 1 over 3. We can verify this by putting in a number. So f1 is -2. And we put f inverse -2, we'll get -2 plus 5 over 3, which is 3 times 1 over 3 is 1. The exact inverse. Another example, let's use h. So we have hx equals 2x squared plus 3. H inverse x, change the subject. We have y equals 2x squared plus 3. Move the 3 on the other side. Y minus 3 equals 2x squared divided by 2. X squared equals 1 over 2 times y minus 3. Now, when we square root them, we need to notice that 2x squared plus 3 is a 1 to 2 function. It's a 2 to 1 function. So you can get the same y value for 2 different x. So here, you need to keep the plus minus sign. So h inverse x is plus minus square root half y minus 3. Verify this by putting the numbers. Let's say h1. 1 squared times 2 plus 3 is 5. Now we put 5 in. Here should be x, sorry. 5 minus 3 is 2. 2 times half is 1. So we'll get 1. Moving on to graphs. So in a coordinate system with y-axis being the vertical axis and x-axis being the horizontal axis, you can mark this relationship or the function on this coordinate system. Let's do a simple one. Y equals x plus 1. So this is a linear equation in the form of gradient intercept form. Y equals mx plus c. And we know that the y-intercept is c here, and the gradient is 1. So it would be something like this. Now move on to harder graphs, like y equals x to the power 3 plus x minus 4. The quickest way is start a table and calculate the points x, y. So let's take 6 points. X with 0, 1, 2, 3, -1, -2. So when we put x equals -2, we'll have -8 minus 2 minus 4, which is -14. We have -1, we'll have -1 minus 1 minus 4, -6. When it's 0, it's -4. When it's 1, 1 plus 1 minus 6, -2. When it's 2, it's 8 plus 2 minus 4 is 6. When it's 3, it's 27 plus 3 minus 4 is 26. Now we plot the points on our coordinate system. -2 here, -14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. -2, 14, our first point here. -1, 6, -6, -1, -1, -2, -3, 4, 5, 6 here. Now 0, -4, 1, 2, 3, 4 here. 1, -2, 1, 1, 2 here. 2, 6, 1, 2, 3, 4, 5, 6, 2, 6 here. And 3, 26. Here's 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26 is somewhere here. Now we connect the graph with lines. So this would be a sketch of y equals x to the power 3 plus x minus 4. We do the same thing with the other graphs. We start a table and calculate the points, mark it on, and connect it with smooth lines. Now move on to inequality. A typical inequality would be something like this. And you can solve it arithmetically, or you can graph it. So for the first example, it's pretty easy to solve. You just minus 2x on both sides. You'll get x smaller than 4. Now for the second inequality, you just see this as two equal signs. So whatever you do to the middle, you will do the same to exactly both sides. So to solve this, we first can see which is plus 2. We'll get -1 smaller or equal to 3x smaller than 9. Then we divide by 3. Remember that when we are dividing a negative number, we flip the sign. But here we're dividing a positive number, so the sign stays the same. So we'll have -1 over 3 smaller or equal to x smaller than 3. Now here is how you graph an inequality on number line. When it's equal to, smaller or equal to, greater or equal to, the dot here is solid. And when it's just smaller or greater, it's hollow. Meaning you cannot take the value here. So x cannot be equal to 1. Now inequalities on coordinate systems on graphs are a bit complicated. You first will graph it with the equal sign. For example, if we have y smaller or equal to x plus 1 and y greater than x. So to our coordinate system, have 1, 2, 3, 1, 2, 3, -1, -2, -3, -1, -2, -3. So we'll first graph y equals x plus 1, which is a graph that looks something like this. And now look at here. If there is no equal sign, the line will be dashed. If there is an equal sign, it will be solid. So here, because it's smaller or equal to, it's solid line. Now we shade the region that is unwanted. So the region is unwanted for y smaller or equal to x plus 1 is where it's greater. And the greater is the top. So we shade the region here. And now for y greater than x, we just graph y equals x with dashed lines. So it would be here. And we shade the region that we don't want, which is below the line, because it's greater than. We don't want the region that's smaller than. So our wanted region here would be the middle part. Now directly and inversely proportion. You can see something like y is directly proportional to x, and it could be like this. This means that the change of x is in ratio with change of y, or you can write it as y equals kx, where k is a constant. Example could say like y is directly proportional to 2x plus 1, and when x equals 1, y equals 5. Find k. So the expression would be y equals k times 2x plus 1. And we know that when x is 1, y is 5. So 5 equals k times 2 plus 1. So we can deduce that k is 5/3. And other one, inversely proportion. So inversely proportion, we still use the same symbol, but now it's 1/x. And it can be written as y equals k/x. You can see some questions like y is inversely proportional to square of 3x. And when x is 2, y is 4. Now this can be expressed as y equals k over 3x squared, because it's square of 3x. And when 1 is 4x is 2. So 4 equals k over 3 times 2 squared, which is 4 equals k over 36. Thus, k equals 144. Now, differentials. Differentials is very important because it can tell you the rate of change of y, the rate of change of x. So you could see something like dy dx, where d here is delta, which is change. You can see this when you are finding the gradient, dy over dx. And this is exactly what we do. So we first will talk about the power rule. So when you are differentiating an expression like 2x to the cube plus 3x squared plus x plus 2, what you do is you times the power with the coefficient and then minus power by 1. So this will be 2 times 3 times x to the power of 3 minus 1 plus 3 times 2 times x to the power of 2 minus 1 plus 1. The coefficient is 1, and the power is also 1. 1 times 1 times x to the power of 1 minus 1 plus, here is actually x to the power of 0. So it's 0 times 2 times x to the power of 0 minus 1. Well, because it's 0 here, so this is gone. So here you will get 6x squared plus 6x plus x to the power of 0 is 1, so just 1. And this is dy dx if y equals. It could be dr dx, dh dx, de dx, anything. This means for the value of x, this is the gradient, the instant gradient of the graph of y. For example, the graph for this would be something like this, right? It's not drawn to scale, the points may not be right, but it's something like this. And the gradient, what we've done is we draw a tangent line and calculate. Well, this is slow and low accuracy. Now we could just find the point. Here, we find the x, we put the x into the differentials, and we'll get the gradient. For example, a linear equation, y equals 4x plus 3. To differentiate this, we'll get just a single 4. Remember the power rule? Which makes sense because the gradient, the m, is just 4. Now, use of differentials. For example, in physics, we could have a displacement time graph. And we know that v equals s over t. So the gradient here, dy dx, is the velocity. When it's a straight line, it's pretty simple. You just calculate the gradient. But what if it's a curve? st. It's a curve and we want to know the instantaneous velocity here. For example, t equals 5. Then we could use we'll just ds dt. We differentiate the equation and plug in t. So we'll get the velocity there. Another use is to find stationary point. For a graph like this could be something like y equals x plus 4 squared minus 2. We want to know the stationary point, which is here. And by completing the square, we could get the vertex form. So we can know that here is -4, -2. But what if we get y equals x squared plus 8x plus 14? Well, this is the same. Well, other than completing the square, you can find the stationary point by differentiating this. Differential of this is 2x plus 8. Very simple, by the power rule. And we set this to 0 because the stationary point, the gradient is 0. M equals 0. And we solve this. Pretty simple. X equals -4. And here we get it. Well, you may say that completing a square is quicker, is easier, but what if the power is greater? What if it's to the power of 4? We want to know the stationary points. What if we have like 3x to the power of 4 plus 2x to the power of 3 plus x to the power of 2 plus -4x plus 3? This is very hard to complete the squares. Complete the So the easiest way is to differentiate. We'll get 12x3, 4 minus 1, plus 6x squared, plus 2x minus 4, because 1 times -4. And then we set this to 0. Solving this, we'll get the 3 stationary points. Now, second differential. When we're dealing with graphs like this, we could have 2x cubed minus 2x squared minus 3x plus 1. We want to know whether this is the local maximum or the local minimum. What do? We do this by second differential. So we know that differential is rate of change. And the first differential is the rate of change of y per x. Now the second differential is the rate of change of the rate of change of y per x. So the rate of change of the gradient. And we notice that the gradient here is positive, positive but decreasing, positive but decreasing, 0, negative, negative but increasing, negative but increasing, 0, positive. So the rate of change of gradient here is negative, it's decreasing, and the rate of change of gradient here is positive, it's increasing. So here, so we know that we can write it by dy d squared y dx squared. So we just dy dx prime, which this also means dy dx. So this equals to the dy dx dx, which will apply the power rule again. So the dy dx, also called y prime, is 6x squared minus 4x minus 3, power rule. Now the derivative, the differential of this, we apply the power rule again. We'll get 12x minus 4. So the graph, to be exact, should be something like this. And we find here, this is about 0.8. So we plug in 0.8, we'll get 9.6 minus 4 is 5.6. We don't need to know the exact number. We just need to know this is greater than 0. The gradient is increasing. So this is a local minimum. Local min. 0.8 something y1 is local minimum. And that's enough. And that's it for today. Thank you for watching.